Look closely at one of the deepest images captured by the James Webb Space Telescope, and the object is easy to miss. Among thousands of distant galaxies, there may be a point of red light no larger than a few pixels. It has no visible spiral arms, no bright jets, and no clear structure. It does not look powerful. It barely looks like an object at all. Yet that tiny mark comes from an age when the universe was still young. Its light began crossing space billions of years before the Sun, Earth, or any human being existed. By the time that light reached Webb, the expansion of space had stretched it into infrared wavelengths. What appears to us as a small red dot is therefore a view into a period only hundreds of millions of years after the Big Bang. That alone would make it valuable. But the first estimates suggested something far more troubling. When astronomers studied several compact red sources in Webb's early observations, some appeared bright enough to contain enormous populations of stars. If most of their light truly came from stars, then some of these objects seemed to possess tens of billions of times the Sun's mass in stellar material. One candidate appeared even larger. The problem was not simply their size, it was the short amount of time available to build them. In the familiar picture of cosmic history, the first galaxies begin small. Gravity draws gas into early structures. Stars form, generations pass, galaxies collide, and larger systems gradually emerge. But these red points appeared during a period when that process had barely begun. They seemed less like young galaxies taking their first steps, and more like mature systems arriving before the universe had time to make them. This tension quickly produced a dramatic idea. Perhaps Webb had found galaxies that should not exist. Perhaps the standard story of cosmic growth was missing something fundamental. The phrase was irresistible because it turned a technical disagreement into a cosmic crisis. A red dot could now be presented as evidence against known cosmic history. Yet the real scientific problem was narrower and more interesting. Astronomers were not debating whether Webb had detected the light. They were debating how that light should be translated into age, mass, and physical structure. Before changing cosmology, they had to determine whether the apparent galaxies were truly made of the stars their brightness seemed to imply, or whether another source was disguising itself as starlight. But a telescope does not directly measure the mass of a distant galaxy. It measures light. Astronomers must then determine what produced that light, how dust and gas changed it, how long its stars have been shining, and how much unseen material may surround it. Change those assumptions, and the same red dot can describe a very different object. That distinction is the key to everything that follows. The early estimates were not foolish, and the observations were not false. The uncertainty lay in the bridge between them. A few red pixels were real. The meaning assigned to those pixels was still being tested. Were they extremely dense collections of stars? Were they powered by matter falling toward black holes? Was their light being altered before it escaped? Or had several different kinds of objects been grouped together because they looked similar from an enormous distance? The little red dots did not immediately prove that the universe was broken. They revealed that astronomers could see a population whose physical identity remained hidden inside unresolved light. Their harmless appearance concealed a much larger question. What process could create so many compact red sources so early? And what would that process reveal about the growth of the first galaxies and black holes? To answer it, we must first understand why these objects remained invisible for so long, and why Webb was able to bring them into view. The little red dots had not suddenly appeared when Webb opened its enormous mirror to space. Their light had been traveling toward us for most of cosmic history. What changed was our ability to receive that light clearly enough to notice the pattern. To understand why, imagine light leaving a distant source while the space between that source and Earth continues to expand. Light travels as a wave. As space stretches during the journey, the wave stretches with it. Its wavelength becomes longer, shifting from the part of the spectrum in which it was emitted toward redder wavelengths. Across the immense distances separating us from the earliest galaxies, this shift can be extreme. Light that began in ultraviolet or visible wavelengths may arrive at Earth in the infrared. This process is called cosmic redshift. It does not mean that every little red dot was literally deep red at its source, like a painted object. The word red describes how its light reaches our instruments after crossing an expanding universe. The amount of stretching also helps astronomers estimate how far back in cosmic history they are looking. Greater redshift generally means the light has traveled from an earlier age. Earlier observatories could study remarkable portions of the distant universe, but the faint infrared signals from these compact sources were difficult to detect and separate. Webb was designed to work in precisely this region of the spectrum. Its large mirror gathers extremely weak light, while its instruments examine infrared wavelengths that carry information from galaxies whose original light has been stretched during its journey. That capability did more than make distant objects brighter. It opened a part of cosmic history that had previously been incomplete. Sources that had been too faint, too red, or too difficult to distinguish could now be detected across several deep observing fields. The first level of discovery came through imaging. Webb's near-infrared camera, known as NIRCam, records how much infrared light arrives in different wavelength bands. From those images, astronomers can estimate an object's brightness, apparent size, shape, and color. When an object remains extremely compact and appears unusually red in selected bands, it becomes a candidate for closer study. But an image, even a remarkably deep one, cannot tell the entire story. A red point may be distant, dusty, dominated by old stars, powered by a black hole, or altered by gas surrounding its source. Different physical systems can produce similar colors when their light is reduced to a few measurements. Imaging can reveal that something unusual is present, without revealing exactly what that thing is. The next level comes from spectroscopy. Webb's near-infrared spectrograph, or NIRSpec, separates incoming light into its component wavelengths. Instead of recording only how bright a source appears through several broad filters, it reveals a detailed pattern of peaks, slopes, breaks, and lines. Those features act as physical clues. They can show which atoms are emitting or absorbing light, how strongly the source has been redshifted, and whether gas associated with it appears calm or disturbed. The difference is similar to noticing a distant light through fog and then passing that light through a prism. The first observation confirms that the light exists and gives a rough impression of its color. The second divides it into a pattern that can be examined. Neither observation automatically supplies an identity, but together, they sharply reduce the range of possible explanations. This distinction also explains why early claims could change as new observations arrived. A candidate first identified in images might appear to occupy one period of cosmic history and contain one kind of stellar population. A later spectrum could provide a firmer distance and expose light that did not behave like ordinary starlight. The object itself had not changed. The evidence had become more precise. Webb was therefore not taking a photograph of the early universe. It was creating a sequence of tests in which discovery through imaging could be challenged, corrected, or strengthened through spectroscopy. As Webb surveyed separate regions of the sky, compact red candidates appeared again and again. Programs including SEERS, JADES, and PRIMER were designed with different fields and scientific goals, yet each contributed examples of these unusual sources. Later observations added more candidates and better spectra. What began as a handful of surprising objects became a repeated feature of Webb's view of the early universe. This repetition mattered. A single strange source might be an unusual galaxy, a misleading measurement, or a rare accident of viewing angle. Finding similar objects in independent surveys suggested that astronomers were seeing a population. There were enough examples to ask how common they were, when they appeared, and whether the same physical process could account for all of them. At the same time, the growing catalogs introduced a new problem. Different surveys did not always select candidates in exactly the same way. One program might emphasize color, another compactness, and another particular spectral features. Some candidates received detailed spectroscopy, while others remained points measured through a few filters. The shared nickname made the collection sound more uniform than the evidence allowed. Webb had therefore delivered a genuine observational breakthrough, but not a finished explanation. Cosmic expansion had moved ancient light into the infrared. Webb had the sensitivity and instruments to capture it. Imaging exposed many compact red sources, and spectroscopy began turning their light into physical evidence. The objects had remained hidden because the required observational window had barely been open. Now that the population was visible, the next task was to decide what qualified an object for the name. Before astronomers could explain the little red dots, they had to establish what, beyond their appearance, these objects truly had in common. Once astronomers could see these sources, they faced a deceptively simple problem: deciding which objects belonged in the same group. The name Little Red Dot sounds as though it describes a known species, like a type of star or galaxy. In practice, it began as a convenient label for a pattern in Webb's observations. The pattern was clear enough to recognize, but its physical cause was not. The first part of the name refers to compactness. In Webb's images, many candidates appear almost point-like, with most of their light concentrated in an extremely small area. When astronomers model their shapes and estimate their effective radii, they often obtain values below a few hundred parsecs. A parsec is a unit of distance used in astronomy, equal to a little more than 3 light-years. Depending on the object, survey, and method, estimated radii may fall below roughly 100 to 500 parsecs. Those dimensions are small for something radiating with the brightness associated with an entire distant galaxy. They are more comparable to a dense galactic core or a large region of intense star formation than to the broad stellar disks familiar in nearby galaxies. Yet the measurements are difficult. These objects lie at enormous distances and may remain only partly resolved. Their true structures can be smaller, more extended, or more complicated than a simple fitted radius suggests. The word little must therefore be handled carefully. It does not mean every candidate has the same dimensions. It does not mean that the complete object would fit inside a planetary system. It means that the observed light is unusually concentrated when compared with many other galaxies seen at similar stages of cosmic history. The second part of the name appears just as straightforward, but red is also more complicated than a surface color. Webb records how bright an object appears across selected ranges of infrared wavelength. Astronomers compare those measurements. A source may be described as red when it becomes much brighter toward longer wavelengths than it is in neighboring, shorter wavelength bands. For many little red dots, however, The full pattern is not simply a steady rise from blue to red. Their spectral energy distribution, which is a map of brightness across wavelength, often forms an unusual shape. The source can appear relatively bright in the portion corresponding to ultraviolet light at its original location. Its brightness then falls or changes sharply around an intermediate region before rising again toward wavelengths that originally belonged to visible or optical light. When plotted, the two rising sides and the lower middle can resemble a broad letter V. This V-shaped pattern is one of the features that made the objects difficult to interpret. The relatively blue ultraviolet side can suggest hot young stars or an energetic central source. The much redder optical side can suggest dust, an older stellar population, or light that has been changed before escaping. One object appears to carry signals that point toward different physical conditions. Part of the change occurs near the Balmer-region, a portion of the spectrum shaped by the behavior of hydrogen. Astronomers often use a strong change around this region to learn about a galaxy's stars, but the same general feature can be affected by several processes. Seeing a pronounced break does not, by itself, reveal whether the light comes from old stars, dense gas, dust, or some combination of sources. It supplies evidence that must be interpreted within a larger model. Spectroscopy added another major characteristic. In many well-observed candidates, hydrogen produces bright emission lines. Helium lines can also appear. These lines form when atoms in surrounding gas release light at particular wavelengths. Some of the lines are broad rather than narrow, meaning their light is spread across a wider range of wavelengths. Broad emission lines often signal gas associated with an active black hole. In familiar systems, gas moving rapidly under a black hole's gravity produces different wavelength shifts depending on whether it is moving toward or away from us. Combining light from that moving gas creates a broadened line. This made black holes an obvious possibility for little red dots. Yet broadness is still an observation before it is an explanation. A line can be widened by motion, scattering, or a mixture of effects. Measuring its width does not automatically reveal which process dominates. That distinction would later become central to the mystery, but at this stage, the spectra established only that many LRDs contained energetic and unusual gas. Brightness was measured. Color was measured by comparing wavelength bands. Apparent size was estimated from the distribution of light, and spectral lines were recorded. Age, mass, composition, and power source were interpretations built from those measurements. Each interpretation might work without being final. If a model assumed that stars produced all the light, it would produce one answer. If another source contributed, the same measurements could lead to another. The evidence had to remain separate from the story used to explain it. Taken together, the observations produced a recognizable profile. A candidate was extremely compact in Webb's images. It showed a strong red rise across selected infrared bands, often combined with a bluer ultraviolet component and a break between them. In cases with good spectra, it might also display broad hydrogen or helium emission. Not every source met every condition with equal strength. Some were selected mainly by color and compactness. Some had detailed spectra. Others did not. Different research teams used different filter combinations, brightness limits, redshift ranges, and definitions. As the catalogs expanded, the boundaries of the label remained flexible. This creates an important separation between classification and identity. Astronomers can group objects because they look similar without claiming they are physically identical. A cloud of dust, a dense stellar system, and an active central engine might produce overlapping parts of the same observational pattern. Distance and limited resolution can hide the differences. The little red dots were therefore neither a random collection nor a fully established species. They shared enough measurable features to demand a common investigation, but perhaps not a single answer. Their compactness, divided colors, spectral breaks, and broad lines formed the evidence baseline. The next step was to test the most familiar interpretation, that most of the light came from stars packed into remarkably young galaxies. The most familiar way to explain a distant galaxy is to begin with its stars. Stars produce much of the light seen from ordinary galaxies, and groups of stars leave recognizable patterns across a spectrum. When the first little red dot candidates appeared, astronomers therefore asked what kinds of stellar populations could reproduce their measured brightness and colors. This process does not involve counting individual stars. At these distances, even Webb cannot separate most of them. Instead, researchers build models containing different mixtures of stars. Some models contain extremely young, hot stars. Others include populations that have been shining for longer. Dust can be added to absorb shorter wavelengths and make the combined light appear redder. The model is then placed at the estimated redshift and compared with the measurements. If one combination of age, dust, and stellar history matches the observed light better than the others, it becomes a possible description of the source. From that description, researchers estimate how much stellar mass is required to produce the brightness. The result is not a direct weight placed on a cosmic scale. It is an inference built from a relationship between mass and light. That relationship changes as stars age. A very young population contains many hot, bright stars and can produce a large amount of light for its mass. As a population develops, its most luminous stars disappear more quickly, while numerous dimmer stars remain. The system may then contain substantial stellar mass without producing the same brightness per unit mass. If the light of a distant source is interpreted as coming from a developed stellar population, the estimated mass can rise. The strong change near the Balmer-region appeared important for this reason. Such a break can be produced by the combined light of stars and may offer clues about their ages. In early models of the compact red candidates, a pronounced break together with the red optical side could be matched by a population that had already formed many stars. The blue ultraviolet side could then be assigned to newer star formation or another less dominant component. This interpretation gave the strange V-shaped pattern a coherent stellar story. An earlier generation of stars supplied the redder light and the apparent break. Younger stars supplied the ultraviolet light. Dust adjusted the colors. If that story was correct, the little red dots were not empty shells or minor stellar groups. They were compact galaxies containing unexpectedly large amounts of accumulated stellar material. Several of the first widely discussed candidates were estimated to lie at redshifts between roughly 7.4 and 9.1. Their light therefore came from a period about 500 to 700 million years after the Big Bang. Under models in which stars dominated their brightness, several appeared to contain more than 10 billion times the Sun's mass in stars. One estimate approached 100 billion solar masses. The numbers were remarkable because of the time available. Before a galaxy can contain stars, matter must gather under gravity. Gas must cool and become dense enough to form them. Many of those stars must then remain while further gas arrives, more stars form, and smaller structures combine. None of these stages happens outside time. Yet the candidate galaxies appeared to have completed an enormous amount of assembly during a small fraction of the universe's present age. The tension was not that any one massive galaxy was forbidden by a simple rule. Cosmic models describe populations and probabilities rather than issuing a list of objects that may exist. The difficulty was producing enough massive systems early enough without demanding an extreme conversion of available matter into stars. If the estimates were correct across the growing population, models of early galaxy formation would need serious adjustment. Public descriptions often compress this careful problem into the claim that Webb had found galaxies that broke the universe. That phrase captured the surprise but removed the conditions attached to it. The observations showed bright, compact, distant sources. The enormous stellar masses emerged only after the light was interpreted through particular stellar models. Cosmology had not been overturned merely because one interpretation created tension with it. The original estimates were still scientifically valuable. Researchers were working with the best measurements then available, and their assumptions were visible and testable. A model is useful not because it can never change, but because it makes clear what must be true for its answer to hold. In this case, the central requirement was that most of the relevant light came from stars. This is a common difficulty when observing the distant universe. A set of brightness measurements may allow several histories to resemble one another. A younger, dusty population can sometimes imitate an older, cleaner one. A brief period of intense star formation can change the ultraviolet side without accounting for the redder light. When the object is unresolved, separate regions are blended into a single signal. The model must divide that signal among possible sources even though the telescope receives it all together. Better wavelength coverage and spectroscopy can reduce this uncertainty, but the first estimates necessarily carried more than one acceptable solution. If another source supplied a large part of that light, the calculation would change. Matter falling toward a black hole can release intense radiation from a compact region. Gas surrounding an energetic source can absorb that radiation and release it again at different wavelengths. Dust can hide one part of the spectrum while allowing another to escape. Any of these contributions can alter the colors and spectral breaks used to estimate stellar age and mass. This does not mean that the little red dots contain no stars. A black hole needs a larger environment in which to grow, and early galaxies can combine stellar and non-stellar light. The question is which component dominates each measurement. If a compact central source supplies brightness that has been assigned to billions of stars, the stellar population can be smaller and younger than the first fit suggests. That possibility changed the meaning of the early crisis. The candidates no longer asked only how the universe had built enormous galaxies so quickly. They also asked whether astronomers had mistaken the light of an unusual engine for the light of a mature galaxy. The stellar interpretation had converted the observed colors into an answer, but the answer remained conditional. Its next test would not come from the brightness alone. It would come from placing the inferred mass inside the measured volume and asking whether so many stars could form, survive, and shine within such a compact region in the limited time available. Once the early mass estimates were placed inside the measured sizes, the stellar explanation faced a harder test. It was no longer enough for a model of stars and dust to match the colors. The proposed galaxy also had to fit inside a remarkably compact region, form within the available cosmic time, and remain consistent with the number of similar sources Webb was finding. Consider the combination, rather than any single measurement. Some early fits assigned more than 10 billion solar masses of stars to objects whose light appeared concentrated within a radius of only a few hundred parsecs. Nearby galaxies can contain dense central regions, and intense star formation can occur in compact spaces. But placing so much inferred stellar mass inside such a small volume pushes the system toward extraordinary densities. The difficulty rises quickly as the radius falls. Reducing a system's width does not merely shorten one dimension, it compresses the same proposed mass across the entire volume. A modest change in the measured radius can therefore produce a large change in the inferred density. Because the most distant sources are only partly resolved, uncertainties in size matter. Even allowing for them, many candidates remain strikingly concentrated. No single number creates an absolute boundary beyond which stars are forbidden. Galaxies contain dense clusters and compact cores, and early cosmic conditions were not identical to those nearby today. The responsible question is not whether nature can ever make a dense stellar system. It is whether stars alone can explain the full combination of mass, radius, brightness, color, spectral features, age, and abundance without requiring several extreme conditions at once. Time supplies the next constraint. Before a large stellar population can shine, matter must begin collecting within growing cosmic structure. Gas must fall into a gravitational well, lose enough energy to become dense, fragment, and form stars. Some of that gas may be expelled by radiation, stellar winds, or violent stellar deaths. More gas must arrive if star formation is to continue. The system must build mass while also responding to the energy released by the stars it has already made. For an object seen only 500 to 700 million years after the Big Bang, every stage must occur early. A model requiring billions of solar masses in stars demands that a large share of available gas be converted efficiently and retained. If many similar objects exist, the explanation must apply across a population rather than to one exceptionally fortunate region. This does not make rapid early star formation impossible. The young universe contained abundant gas, and dense environments can form stars intensely. The tension comes from sustaining enough production in a small enough region soon enough to account for the most extreme stellar fits. Each added requirement narrows the range of histories that can work. Dust complicates the picture further. Dust can absorb shorter wavelength light and help a young system appear red. It can therefore improve a stellar model's match to parts of an LRD spectrum. But dust is not a free adjustment with no physical history. The material must be created, spread through the source, and arranged so that some wavelengths are heavily changed while other light still escapes. In a very young galaxy, that sequence must also happen quickly. Stars must form before some of them can return heavier material to their surroundings. The dust must then survive and mix with gas in an environment filled with intense radiation. A dusty stellar model may reproduce the color, but it inherits questions about how the dust and the required stellar population assembled within the same limited period. The V-shaped distribution adds another layer. Young stars can provide blue ultraviolet light. Older or dust-covered stars can help create a redder optical side. A mixture can produce a sharp change between them, yet fitting each part with a different stellar component can increase the total mass or demand a carefully arranged history. The explanation remains possible, but it becomes less economical as every observed feature requires another extreme condition. Broad emission lines create an independent challenge. Energetic stellar environments can produce strong lines, and not every broad feature requires the same cause. Still, broad hydrogen and helium emission in compact sources naturally invites the possibility of an active central engine. The stellar model must explain those lines, while also accounting for the colors, brightness, density, and short formation time. The abundance of candidates matters as well. Astronomy can accommodate rare objects produced by unusual circumstances. A single dense galaxy might form in an especially favorable region where gas gathered early and star formation proceeded with exceptional efficiency. A repeated population asks for a process that nature can reproduce. As survey fields revealed more compact red sources, an explanation based only on rare combinations became harder to extend to every candidate. This did not require all of them to share one origin, but it strengthened the need to identify which observed properties came from stars and which might come from something more compact. A successful model should not match one color while creating several new problems. If a stellar interpretation required extreme mass, density, dust production, carefully separated populations, and unusual emission lines together, researchers had reason to test whether one missing component could reduce several tensions. It only needed to change the inferred mass substantially. None of this removes stars from the little red dots. These objects exist within developing galaxies, and stars can contribute strongly to their ultraviolet light, chemical material, and surrounding structure. Some candidates may be dominated by star formation. The observational label may include systems in which the balance between stars and another power source differs widely. The stress test, instead, changes the burden of explanation. If stars produce nearly all the measured light, then the largest inferred stellar populations must be accepted together with their compactness and early appearance. If some light comes from a much smaller and more efficient source, the required stellar mass can fall. The galaxy can be younger, less massive, or less densely packed than the initial fit implied. Matter falling toward a black hole provides such a source. Accretion can release enormous energy from a region far smaller than a galaxy. Its radiation can add brightness that a purely stellar model would assign to vast numbers of stars. Surrounding gas or dust can then change that radiation before it escapes, allowing a compact engine to influence the colors and spectral breaks measured across the source. This possibility resolves no mystery by itself. Replacing a difficult stellar model with the word black hole is not an explanation. An active black hole should leave evidence across the spectrum, and its surrounding gas should behave in testable ways. The alternative must account for the observations that favor it, and also survive those that appear to contradict it. The stellar interpretation had therefore been weakened without being eliminated. For many little red dots, stars alone required an unusually demanding combination of rapid assembly, extreme compactness, high efficiency, and complex dust. A central accreting source could reduce those demands, but it created a new problem. If these objects were powered by black holes, why did they not look like the quasars astronomers already understood? An accreting black hole could explain how so much light emerged from such a compact region, but that answer carried expectations of its own. Astronomers already knew many galaxies whose centers were powered by black holes. If the little red dots contained the same kind of engine, they should share at least some of its wider signature. An active galactic nucleus is the bright central region produced when matter falls toward a black hole. The black hole itself releases no light from inside its boundary, but material approaching it can form a rapidly moving flow. Friction, compression, and magnetic activity heat this material before it disappears. A small region can then radiate more intensely than the surrounding galaxy. The most luminous examples are called quasars. They can shine across a broad range of wavelengths. Their spectra often contain wide emission lines from fast gas near the center. Their innermost regions can produce strong X-rays. some launch jets that generate radio emission. Because the flow of matter is uneven and the emitting region is compact, their brightness can also vary over time. The broad hydrogen lines in many little red dots therefore appeared to provide an important clue. In familiar active galaxies, those lines are associated with gas moving rapidly within the black hole's gravitational influence. The compact appearance of the sources strengthened the comparison. A central accreting engine seemed able to provide intense luminosity without requiring every measured photon to come from stars. But the comparison weakened when astronomers looked beyond the infrared spectra. Most observed little red dots were faint or undetected in X-rays. This was difficult to reconcile with a simple picture of exposed accretion, because the hot inner regions of familiar active nuclei commonly release a meaningful share of their energy at X-ray wavelengths. An X-ray non-detection must be described carefully. It does not mean that an object emits no X-rays. It means a particular observation did not collect a signal strong enough to rise confidently above the background. A distant source may produce X-rays that remain below the sensitivity of the survey. Longer observations, or a more sensitive instrument, could reveal emission that a shallower search misses. Distance is only one possibility. Dense material between the central source and the telescope can absorb high-energy radiation. The shape of the surrounding structure can allow light to escape in some directions while blocking it in others. The source itself may produce a different balance of wavelengths from a familiar quasar. Any of these effects could weaken the detected signal without removing the black hole. Radio observations created a related puzzle. Many little red dots were also weak or undetected at radio wavelengths. Yet this absence is not a direct verdict against accretion. Not every active black hole launches a powerful radio jet, and even a genuine active nucleus can be radio quiet. The radio results removed one easy form of confirmation, but they could not settle the identity of the objects alone. Variability offered another test. A compact accreting source can change as the rate and arrangement of infalling material shift. If a large share of an object's light comes directly from a small central region, changes may become visible over repeated observations. Many little red dots, however, did not show the clear variability expected from an ordinary exposed active nucleus. Here again, the limitation of the measurement mattered. Webb had not watched every candidate continuously for long periods. The sources were faint, and observations were separated by practical scheduling limits. Cosmic expansion also stretches observed time intervals from very distant systems. Changes that occur quickly near the source can appear slower to us. If surrounding material absorbs and releases the central radiation, it may further smooth rapid variations before the light escapes. These qualifications did not make the missing signals meaningless. A model cannot answer every non-detection by declaring the source hidden without showing how that concealment works. The amount and arrangement of material must be able to reduce X-rays while allowing the observed infrared light and broad lines to escape. It must also remain consistent with the compact size and luminosity. Each absent signal in the data therefore became a constraint on the environment, even when it could not serve as proof against a black hole. The comparison also depended on what kind of active nucleus astronomers expected to find. Most established quasar templates came from black holes observed at later cosmic times, after their galaxies and surroundings had developed under different conditions. Little red dots appeared much earlier. Their black holes, gas supplies, and host structures might represent a younger phase for which nearby examples were poor guides. The failure of a familiar template could mean that the engine was absent, but it could also mean that the earliest engines had been caught before they became recognizable quasars. The three tests therefore produced an uncomfortable pattern. Broad emission lines and compact luminosity pointed toward active black holes. Weak X-ray detections, limited radio signals, and little obvious variability made the objects unlike the quasars used as familiar comparisons. Neither side could simply be discarded. A rare exception made the situation even more useful. When observations connected an LRD-like source with detectable X-ray emission, astronomers gained a possible view of a related object under different conditions. It was sometimes described as an X-ray dot because it shared several LRD features while revealing high-energy radiation that most candidates concealed or lacked. One exceptional source could not define the population. Instead, it showed that objects with similar infrared appearances might occupy different stages, contain different surroundings, or be viewed along different directions. Some central engines might be more exposed. Others might be deeply covered. Some candidates might include a different balance between stars and accretion altogether. This diversity prevented a simple choice between galaxies and black holes. The little red dots were galaxies or developing galactic systems, so the presence of stars and a central black hole could overlap. The question was not whether one existed and the other did not. It was which component produced the measured light, and why the central activity appeared so unusual. The ordinary quasar template had failed as a complete answer. Scaling a familiar active nucleus down in luminosity did not automatically produce an LRD. The observed combination required broad spectral lines without the expected strength in other channels. If black holes powered many of these sources, either their accretion worked differently, or their light passed through an environment that transformed what escaped. That left the broad lines carrying much of the argument. They had been treated as evidence of extremely fast gas, and therefore as clues to a black hole's mass. But astronomers had mostly focused on how wide the lines were. The contradictions across other wavelengths created a reason to ask a more precise question. What if the shape of each line, not only its width, recorded a different physical process? The broad lines had become one of the strongest reasons to suspect black holes inside the little red dots. Yet that conclusion depended on a hidden step. Astronomers had to decide what made the lines broad before they could use those lines to describe the central engine. An emission line begins with atoms in gas. When an atom releases energy, it emits light at particular wavelengths set by its internal structure. Hydrogen, therefore, produces a recognizable family of lines. In an ideal cloud with little motion and no strong interference, each line would remain concentrated near its expected wavelength. Motion changes the pattern through the Doppler effect. Light from gas moving toward us is shifted slightly toward shorter wavelengths. Light from gas moving away is shifted toward longer wavelengths. If a region contains clouds traveling at many different speeds and directions, their shifted signals overlap. Instead of one narrow mark, the telescope records a wide line. This is the usual interpretation of broad lines around active black holes. Gas close to a massive object moves rapidly under its gravity. Some of it approaches us, some recedes, and some crosses our view at other angles. The combined spectrum spreads across a range of wavelengths. A broader line is then treated as evidence for faster gas. That width can be used to estimate the black hole's mass. The basic logic is familiar from an orbit. At a given distance, an object must move faster to remain bound around a stronger gravitational source. Astronomers use the line width as an estimate of speed and other properties, including luminosity, to estimate the scale of the emitting region. Combining the two produces an inferred central mass. This approach is often called a virial estimate. It does not require astronomers to see individual gas clouds circling the black hole. It turns an unresolved spectrum into a gravitational measurement. When its assumptions are appropriate, it is an extremely useful method. The crucial assumption is that the measured width mainly represents bulk motion. The photons must be leaving gas whose different velocities create the observed spread. If another process broadens the light after it is emitted, then part of the width no longer measures orbital speed. Feeding that altered width into the same mass calculation can make the central object appear more massive than it is. Early applications of the familiar interpretation created another LRD tension. Some broad lines implied black holes that were extraordinarily massive compared with the surrounding host galaxies. The original stellar estimates had already made the galaxies appear too developed. Now the possible black holes could appear overgrown as well. The measurement seemed to replace one early growth problem with another. To test the assumption, researchers needed to examine more than the distance from one side of a line to the other. They needed the full profile, the precise way brightness rises toward the center, forms a peak, and declines into its wings. A simple distribution of many random gas motions often produces a rounded profile. It is strongest near the central wavelength and falls away in a smooth form sometimes described as Gaussian. The exact appearance can be modified by geometry, multiple emitting regions, inflow, outflow, or obstruction, so real lines are rarely perfect. Still, the profile provides evidence that total width alone cannot supply. In some of the highest quality little red dot spectra, the wings did not decline in the rounded way expected from a simple Gaussian model. They extended outward, with a form closer to a double-sided exponential, a central region with long, steadily fading wings on both sides. Beneath those wings, the original emitting component could be considerably narrower. That detail changes the physical picture. If the intrinsic line is narrow, the gas that first emitted the photons may not be traveling at the extreme speeds suggested by the full observed width. Something could be spreading the photons across additional wavelengths after their creation. Some spectra added another clue. Rather than forming one uninterrupted central peak, a line could show a dip or absorption around its center. This type of self-reversal suggests that photons near the original wavelength are being trapped, redirected, or absorbed within surrounding material. It points toward an environment through which the light must struggle before escaping. Free electrons offer a mechanism for producing broad wings. In ionized gas, electrons are no longer bound to individual atoms. A photon traveling through that gas can interact with an electron and be redirected. Because the electrons are moving, the interaction can also shift the photon's wavelength by a small amount. One encounter may create only a slight change. If the gas is dense enough for a photon to interact repeatedly, the small changes accumulate. Some photons emerge, shifted toward shorter wavelengths, and others toward longer ones. A line that began relatively narrow can acquire extended wings even though the emitting gas was not moving at the enormous bulk speeds implied by those wings. This is electron scattering. It does not create the hydrogen line from nothing. Hydrogen gas first emits the light. Scattering then changes the distribution of wavelengths that reaches the telescope. The observed line becomes a record of both the emitting gas and the material through which its photons traveled. The distinction is subtle but consequential. Under the motion-only interpretation, broad wings describe rapidly orbiting or flowing matter. Under the scattering interpretation, they may describe a dense field of moving electrons surrounding a narrower source. The same apparent width can therefore correspond to different velocities and different black hole masses. Researchers can compare these possibilities by fitting the observed profiles. A motion-dominated model may predict one central shape and pattern of wings. A scattering model predicts another, affected by electron temperature, density, optical depth, and geometry. Multiple hydrogen lines can provide further tests because scattering and absorption may influence each line differently. The difference can be understood by imagining a message altered during delivery. In the first case, the spread is already present when the message is sent. Gas moving at many speeds emits photons at many shifted wavelengths. In the second, the original message begins within a narrower range but passes through many intermediaries, each making a small change. The telescope sees the final distribution and must work backward, because the width alone cannot reveal where the spreading occurred or its cause. This also explains why higher signal quality mattered so much. A faint spectrum may reveal that a line is broad while hiding the narrow core, central dip, or exact decline of the wings. With more collected light, the profile becomes detailed enough to separate competing shapes. The improvement does not merely make the same evidence prettier. It exposes information that can reverse the meaning assigned to the width. What once looked like a direct measure of violent motion may instead become evidence of repeated interaction between light and surrounding matter. The highest quality spectra gave strong support to electron scattering for an important group of little red dots. Their extended wings and narrow underlying components were difficult to explain as simple orbital motion alone. This offered a way to reduce the apparently extreme gas velocities without denying the presence of an active black hole. But the conclusion had boundaries. Not every candidate had a spectrum detailed enough for this test. Some little red dots showed different line structures. Analyses of particular objects argued that electron scattering could not dominate every observed hydrogen line. Geometry, outflows, genuine rapid motion, absorption, and scattering may contribute in different proportions. The population could therefore contain a range of environments. Electron scattering was not a universal label to replace the old one. It was a physical explanation supported strongly in a high-quality subset and testable in others as better spectra became available. Even within that subset, identifying scattering created a new requirement. A few free electrons would not be enough to reshape the line so dramatically. The photons would need to pass through a compact region containing a very large column of ionized gas. That material would also interact with radiation at other wavelengths and affect what escaped. The line profile had shifted the investigation from speed to environment. The question was no longer only how fast the gas moved around a black hole. It was what kind of structure could hold enough free electrons to scatter the light repeatedly while producing the extraordinary luminosity contained inside a little red dot. The scattering interpretation demanded an environment unlike the relatively open region imagined around a familiar quasar. A thin cloud containing a few free electrons would redirect only a small fraction of the light. To build the extended wings seen in the strongest spectra, photons needed to pass through an enormous column of ionized material packed into a compact space. At the center of the proposed system sits an accreting black hole. Gas falls inward and releases intense radiation before crossing the point from which nothing can escape. That radiation strikes more gas surrounding the center. When the energy is strong enough, it removes electrons from atoms, turning the material into an ionized mixture of charged particles. The free electrons do not remain still. They move through the hot gas and repeatedly interact with photons trying to leave. Hydrogen deeper within the region can first produce an emission line that is much narrower than the final profile. As those photons travel outward, some encounter one electron, then another, and perhaps many more. Each interaction can redirect the photon and alter its wavelength slightly. By the time the radiation escapes, the narrow original line has been spread into broad wings. The line looks as though it came from gas moving at extreme speeds, even though much of the width was added during the photon's journey. The spectrum carries two layers of information: the conditions where the light was created and the material it crossed afterward. This surrounding structure has been described as a dense ionized gas cocoon. The word cocoon is a physical model, not an object Webb has photographed as a clear shell. The source remains unresolved. Researchers infer the compact material from its effect on the spectrum, the amount of radiation, and the column of electrons required to produce repeated scattering. An important concept here is optical depth. In simple terms, optical depth describes how difficult it is for radiation to travel through material without interacting. A region with low optical depth allows many photons to cross directly. A region with high optical depth forces them to scatter, become absorbed, or follow complicated paths before escaping. The proposed cocoon is highly optically thick at important wavelengths. Photons near the center of a hydrogen line can become trapped or removed from the direct path more strongly than photons in the wings. This can help produce the dip or self-reversal observed in some profiles. The same dense environment that broadens the line can therefore influence its center as well. Repeated scattering also changes the route each photon takes. Radiation no longer travels straight from its birthplace to open space. It may move outward, be redirected sideways, or scatter back toward denser material before eventually finding a path away. This longer and less direct journey gives the electrons more opportunities to alter the observed wavelength. The escaping spectrum therefore depends not only on what the central source emits, but on the temperature, density, shape, and thickness of everything surrounding it. The model is therefore demanding and testable. A cocoon too thin will not create the observed wings, while one too thick may prevent the required radiation from escaping. Its conditions must allow narrow intrinsic lines, scattered wings, central absorption, and high luminosity to coexist. Several measurements constrain the same environment instead of permitting an undefined cloud. Models of the best spectra place this gas on scales measured in light days. A light day is the distance light travels in one day. This is far larger than a black hole itself, but extremely small compared with a galaxy. It describes a compact central environment, not the complete little red dot. That distinction prevents two measurements from being confused. Webb imaging may place much of an LRD's observed light within tens or hundreds of parsecs. The scattering region inferred from spectral modeling can be vastly smaller, only light days across. The larger measurement concerns how the source appears across the image. The smaller one concerns the dense material close to the central engine. Neither scale has been directly resolved in all its internal detail. Once the broad wings are assigned mainly to scattering, the underlying line becomes narrower. Narrower intrinsic lines imply that the emitting gas is moving more slowly than the full profile suggested. Since the motion-based black hole estimate depended strongly on that speed, the inferred mass falls. For the high-quality sample analyzed under this model, the resulting black hole masses lie roughly between 100,000 and 10 million times the mass of the Sun. In ordinary language, These are black holes containing hundreds of thousands to several million solar masses. They remain enormous objects, but they are far below the masses originally inferred when the entire line width was treated as orbital motion. In some cases, the reduction is about 2 orders of magnitude, meaning roughly a factor of 100. A black hole, previously interpreted as hundreds of millions of solar masses, could instead occupy a much younger and lower mass stage. The early universe would no longer need to produce quite the same collection of overgrown black holes implied by the first virial estimates. This does not erase the growth problem. A black hole with 1,000,000 times the Sun's mass is still remarkable when observed early in cosmic history. But the revised range changes the kind of problem astronomers must solve. Instead of explaining only mature giants that already appear out of proportion to their hosts, researchers can investigate a population caught while rapidly building toward larger masses. The luminosity makes that interpretation especially important. If a lower mass black hole produces the measured amount of radiation, it must be feeding efficiently. The models suggest accretion near the Eddington limit. The Eddington limit describes a balance. Gravity pulls gas inward, while radiation produced by the infalling matter pushes outward. In an idealized spherical flow, a particular luminosity creates enough outward pressure to oppose further infall. A source radiating near that level is converting a strong supply of incoming material into energy, while gravity struggles against the escaping light. The limit is not an unbreakable wall. Real accretion is not always spherical, and gas can arrive through uneven flows or short episodes. Radiation can escape more easily in some directions than others. Near Eddington therefore describes the intensity of the inferred growth rather than a universal speed limit that nature can never cross. A young black hole surrounded by abundant gas provides a coherent setting for these conditions. The central engine feeds rapidly. Its radiation ionizes the nearby material. The dense material scatters the hydrogen-line photons, broadening them without requiring equally extreme orbital speeds. The narrower intrinsic lines then support lower black hole masses, while the high luminosity shows that those black holes are actively growing. This picture differs from a mature quasar viewed through open surroundings. The black hole may still be buried in the material that feeds it. The same reservoir that supports its growth also prevents its light from escaping in the familiar form. The redness and unusual spectrum would then be associated with youth and environment, not merely with a smaller version of a later quasar. The model also gives physical meaning to the word hidden. The black hole is not hidden simply because astronomers failed to detect it directly. It is enclosed within gas, whose density is inferred from measurable effects. The broad wings, narrow cores, and central absorption become evidence of the material between the engine and the observer. Even so, the result must remain tied to its sample. The clearest evidence comes from little red dots, with spectra strong enough to reveal detailed line shapes. Many candidates have only imaging or lower quality spectra. Their central engines and surrounding structures cannot automatically be assigned the same properties. Some objects may contain genuine high-speed gas in addition to scattering. Outflows can change the profile. Non-spherical geometry can favor certain directions. Different densities and temperatures can reshape different hydrogen lines. In a population selected partly by appearance, several combinations may produce similar colors and compact images. The cocoon interpretation is therefore a leading physical reconstruction, not a final label stamped onto every red point. For an important high-quality subset, it transforms the broad line mystery. It preserves an accreting black hole, while removing the need for every part of the width to represent violent motion. It replaces apparently mature, overmassive engines with younger black holes growing inside dense ionized surroundings. But a successful explanation cannot stop at one spectral feature. The same objects remain unusually red, compact, weak in X-rays and radio emission, and often less variable than exposed active nuclei. If the cocoon is real, its effects should not end at the hydrogen-line wings. The surrounding material must also explain what happens to the rest of the central radiation before it reaches Webb. The decisive test was therefore broader than the line profile. Could one compact system, an accreting black hole enclosed by dense ionized gas, account for all the separate contradictions that had made the little red dots so difficult to understand? The cocoon model had explained why an emission line could look much broader than the gas motion that first produced it. Its real strength, however, would depend on whether the same environment could explain observations that had seemed unrelated. A useful model should connect the clues rather than repair each one with a separate assumption. The central idea is that Webb may not receive the black hole's radiation in its original form. Matter falling inward produces energetic light close to the black hole. In an exposed active nucleus, a large share of that light can travel outward directly. Inside a dense cocoon, much of it strikes surrounding gas before it escapes. The gas absorbs or intercepts energy, becomes excited and ionized, and then releases radiation of its own. Some photons scatter repeatedly. Others are absorbed and replaced by new photons at different wavelengths. This process is called reprocessing, because the surrounding material converts the central energy into a changed spectrum. Webb would therefore not be seeing a simple mixture of direct accretion light and ordinary starlight. It would be seeing a spectrum shaped strongly by gas between the engine and open space. That difference offers a way to address the first puzzle, the unusual red optical rise. Dense ionized gas can produce powerful nebular emission. Nebular means that the light comes from energized gas rather than directly from the surfaces of stars. When the cocoon reprocesses radiation from the central engine, this gas emission can dominate important parts of the optical spectrum at the source. After cosmic redshift, Webb detects that output in infrared wavelengths. The result can strengthen the red side of the spectral energy distribution without requiring all of that brightness to come from an enormous old stellar population. Hydrogen within the gas also affects the region around the Balmer features. A strong change there may contain contributions from reprocessed emission and absorption, not only a break produced by developed stars. This does not remove stars or make every Balmer-region feature identical. Young stars may provide part of the blue ultraviolet light. Some central radiation may escape or scatter into our view. Dust and gas can alter both components. Different contributions can then form the divided, V-shaped pattern: a relatively blue ultraviolet side, a lower middle region, and a strong red optical rise. The second puzzle is compactness. A central accreting black hole releases intense energy from a region vastly smaller than a galaxy. The dense reprocessing material inferred around it is also extremely compact. That combination can concentrate much of the observed luminosity near the center, making the source appear almost point-like, even when a developing host galaxy surrounds it. The host does not need to be absent. Its fainter and more extended stars may be difficult to separate from the bright central source at such a great distance. Webb's image can therefore be dominated by the compact engine and its immediate environment, while revealing little of the broader structure. The measured compactness becomes consistent with a centrally powered system rather than proof that every part of the galaxy occupies the same tiny volume. The third puzzle is weak X-ray emission. Close to a familiar active black hole, very hot material can generate X-rays. A dense column of gas around the source can absorb much of that radiation or force its energy to emerge in other forms. Depending on the cocoon's shape and our viewing direction, the central X-rays may have difficulty reaching us directly. This gives the non-detections a physical context. They no longer need to mean that no black hole exists. They may mean that the radiation associated with accretion is buried and reprocessed. Yet the qualification remains important. Most results are upper limits, and the exact amount of suppression depends on source brightness, observing depth, gas density, and geometry. The fourth puzzle is weak radio emission. A growing black hole does not automatically produce a powerful radio jet. If these objects represent an early, enclosed stage, their accretion flows may not create the same visible structures as mature radio sources. Dense surroundings or the intrinsic state of the engine may further reduce what is detected. The cocoon model makes weak radio output less surprising, but it does not uniquely predict every non-detection. Radio emission varies widely among active black holes, and the absence of a strong signal cannot determine the structure alone. It works as one piece of consistency rather than a decisive test. The fifth puzzle is limited variability. Radiation produced close to a black hole can change quickly as the inflow shifts, but the cocoon gives different photons different routes. Some escape after fewer interactions. Others scatter repeatedly, travel farther, become absorbed, and are released again. Light emitted at one moment can therefore arrive mixed with reprocessed light originating at another. This mixing can smooth the rapid changes of the central engine. The observed spectrum becomes a delayed and averaged response rather than a direct view of every fluctuation. Short observing baselines, faint signals, and the stretching of observed time by cosmic expansion still matter, so limited variability cannot prove reprocessing. It is nevertheless compatible with the same dense environment inferred from the spectra. One object provided an especially deep test of this picture. The little red dot, known as glimpse 77775, was observed with a spectrum detailed enough for more than 40 lines to be distinguished. Instead of relying on one broad hydrogen feature, researchers could examine many separate indicators of the gas, its density, and the radiation passing through it. Many of those features independently supported a black hole enclosed within hot, dense material. The value of the observation came from convergence. One line might permit several explanations. Dozens of lines, all required to emerge from one physical system, sharply restrict the conditions that can work. The model had to reproduce a network of evidence rather than a single dramatic feature. Glimpse 7775 does not prove that every candidate shares the same architecture. It is one exceptionally informative object. Its spectrum shows what can be learned when the data become detailed enough and demonstrates that a cocooned black hole can account for a rich set of LRD properties in at least a compelling case. This kind of convergence is stronger than solving the same measurement in several ways. The line wings, central absorption, gas emission, spectral shape, and missing high-energy signal arise from different parts of the data. A model that links them must remain consistent across all of those parts. Each successful connection reduces the freedom to adjust the explanation after the fact. At the same time, any future observation that refuses to fit can expose where the proposed geometry, density, or balance of power sources is incomplete. This enables direct testing. The evidence can now be separated by strength. The compact images, unusual spectra, emission lines, and X-ray or radio limits are observations. The presence of accreting black holes inside dense ionized gas is a strong inference for the best-studied sources. The exact shape of each cocoon, the fraction of light supplied by stars, and the model's reach across the full population remain dependent on further modeling and data. Within those boundaries, the cocoon provides explanatory economy. Red optical emission, Balmer-region features, compact luminosity, broadline wings, weak X-rays, radio quietness, and smoothed variability no longer require entirely separate accidents. They can arise as different consequences of one central condition, a rapidly feeding black hole whose radiation must cross dense surrounding material. That unity is powerful, but it exposes the next limit. Little red dots were selected because they resemble one another in distant observations, not because every candidate has undergone the same physical diagnosis. If a cocoon explains the clearest examples, the remaining population may still combine different engines, structures, and stages behind a similar red and compact appearance. The name Little Red Dot had gathered objects into one useful category, but a category built from distant appearance can hide important differences. Two sources may share the same compact shape and red colors while producing that light through different balances of stars, gas, dust, and accretion. This makes a strict choice between galaxy and black hole misleading. A black hole does not float separately from a galaxy. It grows inside a developing system that contains gas and, in most cases, stars. The central engine may dominate one part of the spectrum while young stars dominate another. The balance can change with time, viewing direction, and the amount of material surrounding the center. Hybrid systems are therefore not an escape from the question. They are a realistic framework for interpreting the population. One little red dot may be strongly powered by accretion. Another may contain a weaker hidden nucleus inside a bright star-forming host, and another may be dominated mainly by stars. The task is to determine which explanation best fits each object and how often each kind occurs. For the sources with the highest quality spectra, young accreting black holes inside dense ionized gas currently provide the strongest explanation. The model connects detailed line profiles with compact luminosity, unusual colors, and weak high-energy signals. Its strength comes from explaining several independent measurements through one environment. Its limits remain clear. The exact shape of the surrounding material is uncertain. The fraction of light supplied by stars varies. Many candidates lack spectra detailed enough to reveal narrow line cores or scattering wings. A leading explanation for the best cases cannot simply be copied onto the rest of the catalog. Dusty compact starbursts remain a more familiar alternative. A young galaxy forming stars intensely can appear bright and compact. Dust can absorb shorter wavelength light and create red colors, while young stars contribute ultraviolet emission. This type of model may account for some candidates, especially those without decisive broad-line evidence. For the most extreme objects, however, the old difficulties return. A stellar-dominated model may require very high density, rapid assembly, efficient conversion of gas into stars, early dust production, and an explanation for broad emission lines. It can match parts of the data without explaining the full combination as economically as a cocooned black hole. Stellar-dominated LRDs remain possible, but they are less convincing as a universal answer. A more unusual proposal is sometimes called a black hole star or quasi-star. Despite the name, This is not an ordinary star that has somehow become a black hole. It is a system in which an accreting black hole is buried inside a much larger, massive envelope of gas. Energy from the central accretion supports and illuminates the envelope, allowing the whole object to radiate somewhat like an enormous star. This idea shares features with the cocoon picture, but can describe a more extensive envelope-dominated structure. It may help explain particular spectra that appear difficult to divide into a familiar galaxy and active nucleus. Yet direct confirmation is limited, and it has not been shown that every little red dot passes through such a state. It remains a plausible interpretation for unusual cases rather than the default answer for the population. Short-lived supermassive stars offer another speculative route. A single object containing an extraordinary amount of stellar material could produce unusual luminosity and spectral features before collapsing or changing rapidly. Such objects are theoretically interesting because they might also relate to the birth of massive black hole seeds. Their weakness is the combination of lifetime and abundance. A short phase is difficult to observe frequently unless nature produces enough objects to compensate. The model must also reproduce the detailed spectra and explain why the population appears as common as surveys suggest. Until stronger, distinctive evidence emerges, supermassive stars belong among testable possibilities rather than established explanations. Some proposals focus less on the immediate light source and more on the environment that created the compact system. A dark matter halo with unusually low spin contains gas with relatively little angular momentum. Instead of remaining spread across a broad rotating structure, the gas can collapse more directly toward the center. This may help produce the compactness and abundance of early dense objects. Low spin does not by itself explain what powers the observed radiation. The collapsed gas might feed a black hole, form stars, or create a mixture of both. The halo model can therefore complement a cocooned black hole interpretation by explaining how material became so concentrated. It should not be presented as a competing luminous engine when it addresses a different stage of the problem. Links to globular cluster progenitors or related compact stellar systems have also been proposed. Dense early stellar environments could connect LRD compactness or number evolution with structures seen later. But this possibility does not yet reproduce the strongest broadline and reprocessing evidence. It remains a lower confidence clue about possible descendants or associated environments. These models should not be judged by how dramatic they sound. A strong explanation must account for several independent observations, avoid excessive special adjustments, make predictions that differ from its rivals, and survive new spectroscopy or observations at other wavelengths. A proposal explaining only redness is weaker than one that also predicts line shapes, high-energy behavior, size, and evolution. Future tests must separate models, not merely collect examples. Detailed hydrogen lines can test whether scattering or fast motion dominates. Deeper X-ray and radio observations can reveal hidden central activity or place stricter limits on it. Better imaging can separate an extended host from compact central light. Carefully selected samples can show whether one model explains most objects or only an unusual subset. A useful theory must risk being wrong by predicting which features should appear together. Without that risk, almost any dense and distant source could be adjusted after observation to resemble an LRD. Population diversity can actually make the science more informative. If LRDs include several physical systems, their differences may reveal stages of early assembly. One object may show a black hole still deeply buried in its fuel. Another may be emerging from that material. Another may show a compact stellar system before central accretion becomes dominant. Their shared appearance could mark overlapping conditions rather than one permanent species. The most cautious synthesis is therefore also the most useful. Little red dots probably form a mixed observational population, but rapidly growing black holes appear to play a major role in many of the best-studied cases. Stars, gas, and accretion are not rival ingredients that must be separated completely. Their changing balance may be the defining feature. That conclusion resolves the question of present power only partly. Even if a young black hole is feeding inside the dot, it must have come from something smaller. Its cocoon can explain how the object looks, but not how the central seed formed or gained so much mass before the universe was 1 billion years old. If many little red dots contain young black holes in a period of rapid feeding, their unusual appearance captures only one moment in a longer history. Every central black hole must have begun with a smaller seed, and the early universe allowed little time for that seed to grow. The final mass depends on more than age. It depends on how massive the seed was at birth, how quickly matter reached it, how often the supply was interrupted, and how much incoming gas was driven away by the energy released during accretion. Different combinations can lead to similar masses, which makes the starting point difficult to recover from the finished object. One broad possibility begins with light seeds. The earliest generations of massive stars lived quickly and could leave black hole remnants after their deaths. These remnants would be large compared with ordinary stellar black holes in some cases, but they would still begin far below the masses inferred for active black holes in LRDs. A light seed therefore needs many rounds of growth. Gas falls inward, joins the black hole, and increases its mass. As the black hole becomes larger, it can support a larger inflow under favorable conditions. Growth can compound. The increase during a later period can exceed the increase during an earlier one, because the object receiving the fuel is now more massive. This means a modest seed can, in principle, become enormous without adding the same fixed amount each year. But the process requires time and continued access to gas. If feeding repeatedly stops, if radiation drives material away, or if the surrounding galaxy cannot deliver fuel to the center, the seed may fall far behind the mass required at the observed age. The second broad family begins with heavy seeds. Under special conditions, a large concentration of gas may collapse toward a central object without first turning most of itself into ordinary stars. Related pathways can create a black hole or precursor with a much larger initial mass than a stellar remnant. The seed receives a head start and needs fewer stages of later growth. That advantage comes with a different uncertainty. The required conditions may be rare. Gas must lose support and angular momentum while avoiding processes that would divide it into a normal stellar population too early. Heavy seeds are therefore attractive solutions to the limited cosmic clock, but their existence in a particular LRD cannot be assumed simply because they make growth easier. Both families still require accretion. The near-Eddington luminosities, inferred for cocooned black holes, indicate intense feeding. At approximately this level, the inward pull of gravity and the outward pressure created by radiation approach the balance described earlier. Maintaining rapid growth means continuing to move gas inward, even while the energy released by that gas resists further supply. The comparison between seed models is a comparison of complete histories, not starting masses alone. A heavy seed that rarely feeds may remain smaller than a light seed supplied continuously. Conversely, rapid early accretion cannot help a seed that forms too late. Birth time, initial mass, fuel, and feedback must be evaluated together against observation. The dense environment of an LRD may help explain how this occurs. The cocoon is not only something that hides or reprocesses radiation, it may be connected to the reservoir feeding the black hole. Large amounts of gas close to the center can support rapid accretion while also creating the electron-rich material recorded in the spectrum. Yet the same radiation that ionizes the gas can heat it, push it outward, or open channels through it. Feeding may therefore occur in episodes rather than as one perfectly steady flow. A black hole can experience an intense period of growth, enter a quieter interval when fuel is disturbed, and begin feeding again when fresh gas reaches the center. Episodic growth complicates any simple calculation based only on the object's age. A black hole observed during a luminous LRD phase may be near the peak of its activity rather than representative of its average history. To determine whether a light or heavy seed can reach the measured mass, researchers must consider how long such active phases last and how often they return. Accretion may also exceed the idealized Eddington balance for limited periods. A real flow can be uneven, thick, or concentrated into particular directions. Radiation may escape through less dense paths while matter continues arriving elsewhere. Under those conditions, the mass inflow can temporarily exceed what a simple spherical model suggests. This is called super-Eddington accretion. It offers a way to accelerate early growth, especially for a light seed facing a short deadline. But it should not be turned into an automatic answer. The duration, efficiency, and stability of such episodes remain important, and the spectra do not prove that every LRD has spent its history above the Eddington rate. The diversity of LRD black hole estimates may preserve several stages of this process. The scattering analysis of a high-quality subset points toward masses of roughly 100,000 to 10 million suns. Other objects can occupy a higher range because their measurements, structures, or evolutionary states differ. Able 2744 QS01 provides a striking example. This LRD-associated system is observed at a time roughly 700 million years after the Big Bang. Measurements of gas motion around its center indicate a black hole of approximately 50 million solar masses. Rather than inferring mass only from a broad, unresolved line, the observation uses the movement of gas across the central region to constrain the gravitational source. This case shows that at least some early black holes had already become highly developed. It does not mean every little red dot contains a 50 million solar mass object. Nor does it cancel the lower masses inferred when electron scattering is included in a different spectral sample. The objects may represent distinct masses, environments, and points along a growth sequence. The result strengthens the origin problem without selecting one solution. A heavy seed could reduce the amount of growth required. A light seed could succeed through sustained near-Eddington feeding, unusually frequent active episodes, or periods above the idealized limit. Mergers and changing gas supplies may also shape individual histories, but no single pathway follows uniquely from the observed mass. Little red dots, therefore, act as constraints on early black hole formation. Their numbers, masses, luminosities, and cosmic ages determine which proposed seeds and feeding histories remain plausible. The better these properties are measured, the less freedom a model has to delay formation or assume unlimited fuel. What the observations may be revealing is not one birth mechanism, but a stage when several histories become visible in a similar way. Different seeds can enter dense, rapidly accreting phases. Their radiation becomes trapped and reprocessed, producing the compact red appearance by which Webb finds them. The remaining question is what follows. If the cocoon marks a phase, rather than a permanent kind of object, the black hole, gas, stars, and host galaxy must continue changing. Some systems may shed their covering and emerge as more familiar active nuclei. Others may fade. To understand the meaning of the population, the red dots must be followed forward into the galaxies and quasars they might become. A little red dot may not remain a little red dot for long. If its appearance is created by rapid accretion inside dense surrounding gas, then the name describes a condition rather than a permanent species. Both the fuel and the object consuming it will change. The population itself offers a clue. LRDs become prominent during the early periods explored by Webb, but their observed abundance appears to decline toward later cosmic times. This does not necessarily mean the objects vanish. They may change their appearance and no longer satisfy the colors or compactness used to select them. Survey limits also matter. Astronomers compare samples built with different instruments, depths, wavelengths, and selection rules. A source easy to recognize at one redshift may enter or leave a catalog at another because different parts of its spectrum move through the observing filters. The decline is therefore evidence of evolution, but its exact scale remains tied to how consistently the population is measured. The cocooned growth picture supplies a physical reason for change. As the black hole feeds, its radiation heats and ionizes nearby gas. Some energy is trapped and reprocessed, but some can push against the surrounding material. Outflows may carry gas away, and less dense paths can open through the covering. The fuel reservoir also evolves. Gas falling inward can be consumed by the black hole or turned into stars. Radiation and winds can rearrange it. Fresh material may arrive from the larger galaxy, while mergers can disturb the system and deliver new supplies. The cocoon can thicken, become uneven, or begin to clear. As clearer paths form, observers may receive more direct radiation from the center. X-rays that were once absorbed may become easier to detect along some directions. Changes in the accretion flow may appear as stronger variability because less surrounding material smooths the signal. The red spectrum produced by reprocessing can weaken as a greater share of central light escapes without being converted. An object selected as an LRD during its buried stage might then resemble a more familiar active galactic nucleus. If the black hole continues growing and becomes extremely luminous, the system could enter a quasar-like phase. The change would not require one object to become another species. It would reflect the same central engine seen through a changing environment. The host galaxy changes at the same time. Stars continue forming, and the galaxy can gain matter through gas inflow and mergers. An extended stellar structure may become brighter and easier to resolve. As central accretion rises or falls, the balance between the nucleus and the host shifts. A source once dominated by compact reprocessed light may later appear as a visible galaxy with an active center. Not every system must follow this path. Some black holes may exhaust or lose their fuel and enter quiet periods before becoming exposed quasars. Later inflow may awaken them again. Some candidates may have been dominated by stars from the beginning. Different seed masses, environments, and feedback histories can produce different outcomes while sharing a temporary red appearance. Viewing direction can make those outcomes look more varied than they are. An uneven cocoon may contain open channels beside dense walls of gas. An observer aligned with a clearer path could detect more direct central radiation, while another direction through the system would remain red and reprocessed. Two objects at similar physical stages might therefore enter different catalogs because their surroundings present different paths to the telescope. Duration is important. If the LRD appearance lasts only a short time, finding many examples implies that many early systems must enter the phase. If it lasts longer, fewer systems could account for the observed population. The number of dots, their redshift distribution, and the fraction showing clear accretion signatures therefore constrain how common and persistent the buried growth stage can be. This connects individual spectra with the history of black hole and galaxy assembly. Lower redshift analogs provide one way to test this interpretation. These are systems observed at later cosmic times that reproduce important LRD features while allowing astronomers to see more of their structure. They cannot recreate the early universe, but they can show how distance and observational limits change the appearance of a known galaxy. One example has been nicknamed the Saguaro. It is a lower redshift spiral galaxy containing a highly active central black hole. At its actual distance, the extended host can be studied. Its spiral structure and central activity are not compressed into the same unresolved point. Researchers can take the measured light of this galaxy and calculate how it would appear if placed much farther away at an earlier observed redshift. This process is sometimes called synthetic redshifting. It accounts for changes in apparent size, wavelength, and surface brightness to predict what a distant instrument would recover. The exercise does not physically move the galaxy through time. It asks how much of the known system would remain visible under conditions similar to those affecting an early source. The answer is revealing. Much of the extended host becomes difficult to detect. The concentrated central region remains, and the system can take on a compact red appearance resembling a little red dot. This supports an important possibility. Some LRDs may not be tiny isolated objects with no larger host. Their galaxies may be present, but too faint and spread out to compete with the bright center in current observations. The compact classification can be partly an effect of which component remains visible across immense distance. The Saguaro comparison also supports the idea of an active phase. A galaxy with a developed host can temporarily look LRD-like when its central black hole dominates the measurable light. Earlier galaxies could pass through a similar observational state while their black holes feed intensely inside dense gas. But resemblance is not ancestry. Saguaro is not a proven descendant of a particular early LRD, and synthetically shifting its light does not demonstrate that every red dot contains a spiral host. The early universe had different gas supplies, stellar populations, and assembly conditions. The analog shows that the proposed transformation is possible, not that it is universal. A complete family tree requires more evidence. Astronomers need samples selected in comparable ways across cosmic time. They need deeper imaging, capable of separating faint host light from central emission. Black hole masses and stellar masses must be measured without assigning the same photons to both components. Population statistics must connect the abundance and duration of the early phase with plausible later descendants. Until those links are established, the evolutionary picture remains a strong inference rather than a direct sequence observed from beginning to end. The decline of LRD-like sources is measured with qualifications. Changing cocoons and active phases provide a physical interpretation. Lower redshift analogs demonstrate how a host can disappear from a distant image. The exact path of each object remains unknown. Even this incomplete picture changes what the red dots mean. They need not represent galaxies that appeared fully formed and remained permanently strange. They may capture a brief interval when black hole growth, dense gas, and limited resolution combine to make a developing galaxy look like a tiny red source. The investigation had now moved from pixels to spectra, from spectra to an ionized cocoon, and from the cocoon to a possible cosmic life cycle. Enough evidence had accumulated to answer the title directly. The answer, however, had to preserve the difference between what Webb measured, what the strongest models inferred, and what the larger population had not yet revealed. The little red dots can now be answered without turning uncertainty into failure or a leading model into universal fact. The evidence does not point toward objects that have broken the universe. It points toward a stage of growth that earlier telescopes could barely see and that familiar galaxy models were not built to describe. What Webb observes directly is clear. These are distant sources whose light comes from the early universe. They appear compact and unusually red across selected infrared wavelengths. Many show divided spectral shapes, strong changes around the Balmer-region, and broad hydrogen or helium emission lines. Across the population, those features occur in different strengths and combinations. These measurements establish the mystery, but they do not name the engine. The first dramatic interpretation treated much of the red optical light as coming from stars. Under that assumption, several sources appeared to contain enormous stellar populations, only hundreds of millions of years after the Big Bang. The resulting tension was real, but conditional. Packing the inferred stars into such compact regions required extreme densities and rapid assembly. Producing the colors demanded carefully balanced populations and dust. If most of the brightness was not ordinary starlight, the apparent ages and stellar masses could fall. Accreting black holes offered a compact source of immense energy. Their presence also seemed consistent with broad emission lines, yet ordinary exposed quasars created another mismatch. Most LRDs remained weak or undetected in X-rays and radio observations, and many did not show obvious rapid variability. A black hole could explain the luminosity, but not if it behaved exactly like the later active nuclei used as templates. The decisive change came from treating the spectral lines as shapes rather than simple widths. In high-quality spectra, long wings could surround a much narrower intrinsic component. If the entire width represented fast orbital motion, the gas and inferred black hole had to be extreme. If repeated interactions with free electrons added much of the width, the original gas could be moving more slowly. That line profile evidence led to a physical environment. A rapidly feeding black hole can ionize dense gas around itself. Photons created inside that material scatter from moving electrons, become absorbed, and travel through indirect paths before escaping. Hydrogen lines acquire broad wings. Central photons can become trapped. The radiation reaching Webb no longer resembles the direct output of an exposed accretion flow. The same gas can reprocess central energy into strong nebular emission. That emission strengthens the red optical side of the spectrum and contributes to Balmer-region features. Stars or a smaller amount of escaping central light can supply part of the bluer ultraviolet side. The compact engine dominates the image, while a fainter host remains difficult to resolve. Dense material also gives context to the missing signals. X-rays can be absorbed or forced to emerge in other forms. Changes from the central engine can be smoothed as photons take different routes and are released at different times. Weak radio emission becomes less surprising if the young accretion state does not produce a powerful visible jet. The pieces no longer stand as separate coincidences. Redness, compactness, broad wings, Balmer features, weak X-rays, weak radio emission, and limited variability can arise from one central condition: energetic accretion enclosed within dense gas. This unity is why the cocoon interpretation carries more weight than a model designed only to reproduce a red color. Each clue arises from a different measurement, yet all respond to the same surrounding material. If future observations break one of those connections, the model must change. For the clearest present spectra, however, the agreement provides a coherent physical answer instead of a collection of unrelated adjustments alone. The direct answer is therefore this: for many of the best observed little red dots, the source is red because radiation from a rapidly growing black hole is scattered, absorbed, and re-emitted by the dense material surrounding it. It looks little because much of the detectable luminosity comes from an extremely concentrated central system, while the larger host galaxy may remain faint or unresolved. The appearance may mark a young, buried stage of black hole growth. This answer has levels of confidence. The compact images, colors, line profiles, and multi-wavelength limits are observations. The presence of accreting black holes in dense ionized environments is the best supported inference for several high-quality cases. The exact geometry of each cocoon, the amount of light supplied by stars, and the balance between scattering and genuine gas motion remain model-dependent. Important questions are still open. Not every candidate has decisive spectroscopy. Some may be dominated by star formation, and others may combine several sources of light. The fraction containing strongly accreting black holes is not known exactly. Their seeds may have formed through different pathways, and no complete family tree connects every early LRD with a later galaxy or quasar. Population diversity does not weaken the central discovery. It changes its scale. Webb may not have found one new species with one rigid definition. It may have uncovered several versions of a physical period that was difficult to observe before, the interval when central black holes, young stars, and dense gas grew together, with the gas hiding and transforming the energy released at the center. The earliest mass estimates were therefore not meaningless, and the later interpretation does not simply erase them. Those estimates exposed a contradiction that demanded better data. Better spectra then revealed that the light could not safely be assigned to stars alone, and that broad lines could not automatically be translated into orbital speed. The universe did not fail the measurement. The interpretation improved. Standard cosmology is not overturned by the presence of the little red dots. Their corrected masses and mixed power sources reduce the most dramatic conflict with the expected amount of early structure. But the objects still matter, because they show that black hole and galaxy assembly operated rapidly in environments of extraordinary density. When the cosmos was only a small fraction of its present age, gas had already gathered into compact regions, stars were forming, black holes were feeding intensely, and radiation was reshaping the material that supplied that growth. The process may have been more efficient, more hidden, and more varied than earlier observations suggested. This is the scientific significance behind the title. The dots exist for a reason, grounded in known physics. Gravity concentrates matter, accretion releases energy, and dense gas transforms the light before it escapes. The remaining uncertainty concerns how often this sequence occurs, how its geometry changes, and which paths lead into and out of it. The answer removes the false terror of a broken universe, but it leaves something more restrained and more real. These objects reveal how quickly cosmic matter learned to organize itself around growing black holes. If they are not threats, and if they do not overturn physics, then what about that discovery should still unsettle us? What remains truly unsettling is not danger. The ancient little red dots are not moving toward us, and their light does not carry a warning about an approaching event. Whatever happened inside them had already unfolded long before Earth formed. They are not evidence that nature stopped following its own rules. Gravity still gathered matter. Gas still responded to pressure and radiation. Atoms still absorbed, scattered, and released light. The mystery became clearer precisely because known physics could connect the separate observations once astronomers identified the right environment. Nor do the dots prove that the universe should not exist. The first mass estimates created a serious scientific tension, but they depended on assigning most of the measured light to stars. Better spectra revealed that some of that light could come from energetic accretion and dense gas. The apparent crisis became a lesson in how differently one unresolved source can be interpreted. The real unease begins after those dramatic claims are removed. Cosmic youth sounds like simplicity. We imagine an early universe containing little more than expanding gas, scattered young stars, and small structures beginning a slow climb toward the galaxies seen today. The little red dots reveal a more active beginning. Within a small fraction of the universe's present age, matter had already gathered into dense regions. Stars were forming. Black holes had appeared and gained mass. Gas was falling inward, while radiation pushed outward. Material surrounding the central engines was being ionized, heated, moved, and transformed. Several processes that shape mature galaxies were already interacting within compact young systems. The black holes were not waiting for their galaxies to become complete. In at least some cases, central growth was advancing while the surrounding host remained difficult to see or was still developing. The relationship between black hole and galaxy was being built in motion rather than added after everything else was finished. It would be too strong to claim that the little red dots alone determined the galaxies that came later. Their exact descendants remain uncertain. Yet later cosmic structure emerged downstream of an era in which these hidden growth phases occurred. The mature galaxies of later times inherited a universe already shaped by early stars, accreting black holes, energetic radiation, and repeated exchanges between central engines and surrounding gas. The discovery also changes the meaning of scale. In a Webb image, an LRD may occupy only a few pixels. It has no visible face, no clear boundary, and no internal story written across the picture. The image can make the object seem almost empty because distance has compressed its complexity into a point. But small in an image does not mean physically unimportant. Inside that point may be a black hole feeding from dense gas, an ionized environment trapping and reworking its radiation, and a faint host galaxy growing beyond the light that dominates our view. The apparent dot is the final compressed record of processes occurring across very different scales. Its redness is also not one simple color. It is the result of radiation created near stars or an accreting black hole, changed by hydrogen, electrons, dust, and geometry, stretched by the expansion of space, and collected after an immense journey. The red signal is not merely how the object looks. It is what remains after matter, distance, and time have altered the light. There is a human lesson in the correction, though it is not a new law of physics. The earliest interpretation attracted attention because it suggested that the universe had made impossible galaxies. The later evidence did not make the objects less remarkable. It replaced a louder mystery with a deeper one. Science advanced by allowing the first answer to remain conditional. Images supplied candidates. Spectra exposed assumptions. Detailed line shapes changed the meaning of broadness. Non-detections became constraints on hidden environments. Each correction reduced one form of certainty while revealing a more coherent physical history. The remaining uncertainty is part of that history. Astronomers do not yet know whether every LRD contains an accreting black hole, how many are dominated by stars, which seeds began the growth, or what each source eventually became. Those gaps do not restore the claim that anything is possible. They define the observations needed to distinguish among limited, testable explanations. Return, then, to the original deep field image. Thousands of distant sources fill the frame. Somewhere among them sits a tiny red mark, still lacking visible spiral arms, jets, or a clearly resolved cocoon. Nothing about the few pixels announces what they contain. At the beginning, that absence of detail made the dot seem threatening because its brightness appeared to demand a galaxy assembled too early. Now the same absence carries another meaning. The object may be hiding its most important component behind the material that feeds it. Its simplicity belongs to the image, not to the physical system. The dot may capture a young black hole during one of the periods when it gained mass most intensely. Dense gas close to the center may be scattering its spectral lines and converting its energy into the red light Webb detects. Fainter stars may surround it beyond the unresolved central glow. An entire stage of galactic development can disappear into one point. That is what makes the discovery unsettling. It reveals that complexity did not wait for the universe to become old. Growth, concealment, feedback, and transformation were already operating while cosmic history was still near its beginning. The quiet red pixels are evidence of how quickly gravity turned simple material into systems capable of reshaping their surroundings. The dot was never terrifying because it broke the universe, but because it revealed how quickly the universe learned to build monsters.